Hello and welcome to another video. In this video, we're going to be doing the third problem of Saturday's weekly contest, and it's going to be minimum cost to convert string. And so you're given zero index strings, source and target. Both of them have length n, and they consist of lowercase letters. You're also given two zero index character arrays, original and changed, and an integer array cost, where cost represents the cost of changing a character from original to changed. And you start with the string source. In one operation, you pick a character from the string and change it to the character y at a cost z if there exists an index that's possible, and return the minimum cost to convert the string source to string target. If it's impossible, return -1. So for example, when we have a, b, c, d, we want to convert it to a, b, c, e. So we have a, b, c already. Now we just need to convert d to e. So we can actually see if that's possible. Well, actually, wrote this a little wrong, so we actually want to convert it to ACBE. Yeah. So ACBE. So this is done. Now we need to convert the B to the C. So B to C conversion costs us 5. And C to B conversion costs us 5. And D to E costs us 20. So actually, I think I missed something. So yeah, so you don't want to convert C to B directly. You want to convert C to E first, which only costs us 2, or which only costs us 1, and then you want to convert E to B. So you would convert the C to an E, and then you would convert it to a B. So that's why it's not so simple as just like look up the cost, because there might be a cheaper way to do it. So this costs us 3 total. And so this is 28. In the second one, we want to change all A's to all B's, and we have to change basically A's to C's and then C's to B's. So we change the A's to C's and then we change C's to B's. So each one of those conversion costs us 3. So then we have 4 letters and we have 12 here. And in the next one, we can't convert because this is impossible, because we can only change A's to E, so we can't change like the D to E, for example. So this is impossible. So let's go back to example 1, actually, and let's delete the rest of it. So let's just take this, delete the rest of it, and this is the one we're going to walk through and figure some things out. So let's first actually, like, now that we realize we aren't always going to want to convert directly, right? Like here, you don't want to convert directly from the letter C to the letter B, I believe. Yeah, you don't want to just convert C to B because that costs us 5. And it's cheaper to convert in some other path. So let's start off by drawing this original changed graph, and then we can figure some stuff out. So we'll have original changed graph. So we'll have A, and there's a path to B with cost 2. Then there's B, path to C with cost 5. And then there's C to B. B with cost 5. And then let's see what else. There's C to E with cost 1. So C to E with cost 1. So we can, whenever you have this kind of thing, whenever you go from one to the other, you can always draw a directed graph. And kind of a couple more. So E to B with cost 2. So E to B with cost 2. And finally D to E, I believe. Let's see, D to E with cost 20. D to E. Okay. And so essentially, once we can even delete this now, like no matter what we have, we're always going to have some graph like this, right? We're going to have some graph like this. And you basically want to know, like, let's say I want to convert A to D. You basically want to know the shortest path. Like this is how you can get from an edge to an edge. If you want to convert A to D, so if we want to convert x to y, we need shortest path from x to y, if it's possible, right? So in this case, we can't convert to D because you see, like, there's no air going into D. But if it was possible, like, for example, let's say we can convert, like, this is possible, right? A to E. So the shortest path would be, we'd have to go A to B, and then we'd have to go B to C, it looks like, and then we have to go this way. So the shortest path would be something like this. Be 8. Now in the constraints, by the way, notice, so all of these edges, like let's say we have an edge from x to y, we can't have we can actually have duplicate edges because they said that there are 2,000 edges possible. So if there's 2,000 edges possible, this is pretty easy to fix. And this is similar to the branch closing problem. What's going to happen is you will have duplicate edges because if you have 26 letters times 26 letters, that's like 500 something, right? You have to have duplicate edges. There's like no way around it. Like even if you have edges there and edges back, right? There's no way around it. So you will basically always have duplicate edges. So let's say we have like an edge that's A to B that's 2, and then an edge A to B that's 20. Like it's very easy to solve this problem. We can just keep track of what our edge is currently, right? So if we don't have the edge, put it in. If we do, just keep minimum distance, right? So that's very easy. While we're making the graph, we can just like, if we have 2 and we're trying to put in 20, we just will never put it in because that'll never be used. Similarly, if we have 20 and we're trying to put in 2, we'll just replace 20 with a 2. So now we'll have like a directed graph with no duplicate edges, but it might have cycles, it might have like all kinds of other stuff. Now what we can do is we can pre-compute from every single point, like from A, we can pre-compute the shortest distance to every other point. And you can do this either using Dijkstra's or you could use Floyd-Warshall. So I haven't used Floyd-Warshall much, so I just usually stick to Dijkstra's, and Dijkstra's can do pretty much all the same thing as the other stuff. And Dijkstra's time complexity for getting every single point to every other point is something along the lines of v cubed log v, and Floyd-Warshall would just be v cubed, but because log v here is log 26, that's basically nothing, so it's going to be the same time complexity. So essentially we'll say like, okay, from A, we will run Dijkstra's to every single point, and it's pretty straightforward to run Dijkstra's to every single point. Instead of just stopping once you get to one point, you just maintain a heap, and as long as your heap is not empty, you just keep going and going and going and going. So what that's going to look like is like, we'll start at A, we'll put it into the heap, then we will put in B, and then when we put in B into the heap, we will put in like paths from B and so on and so on and so on. And so what's going to happen at the end, if we actually calculate these, we'll say like, once we actually get this, so we'll have like A to B, which will be length 2, then we'll have A to C, which will be length 7, then we'll have A to D, which isn't possible, so that's not going to be in our graph. And then we'll have A to E, which will be, let's see, the shortest path here is 8, I believe. Yeah. And we do this for every single point, right? So our graph, our like, first we have the normal graph, and then we'll have a modified Dijkstra's graph. So we have a modified Dijkstra's graph, and it will just have, it'll be a dictionary of dictionaries that will be, so dict of dicts, and the dictionary is going to be in the format of start node, end node, and path length, right? And then it's going to be really easy because, so essentially for every start node, it will have a dictionary of all end nodes it can go to, and then the value will be the path. Now when we try to convert some strings, let's say we try to convert like some string like this to some string like this, or let's just make it not so bad. So let's say we can try to convert like A, B, C, D, E to B, C, D, E, F. So before, we couldn't just always take the direct node, and that might not exist. Like, we can't just say, like, what's A to B, and let's just always go that way, right? Because there might be some faster way. You might want to convert A to E first or some other thing. But now with Dijkstra's, we are pre-computing all of our shortest paths, so we can just look through it, and we could say, like, okay, is there an A to B? If there is, let's get that value, and that's guaranteed our shortest value. Then let's go to the next value. Is there a B to C? If there is, let's get that value, and it's the shortest value. And if a value doesn't exist, that means we can't go from X to Y. So we just return -1 or whatever the problem asked. And if you look at the constraints, so if you have this graph, our original graph is gonna have like start edges and end edges. So that's gonna be something like 26 by 26, right? And our Dijkstra's graph is also gonna be 26 by 26. So to go from a 26 by 26 graph to a Dijkstra's graph is going to be 26 cubed log 26, which is like a really small number, right? It's like 500 times 26, which is like, I don't know, like 7,500 or something. Could be wrong about that, but regardless, it's going to be easily less than the array length because the array length is like 10 to the fifth. Now you could do this without pre-computing. You could actually just like every time you check a letter, you could just run Jigsters on it. So you could like do this. You could say like, okay, let me just run Jigsters on B to get to see like what is it, and that, you can actually just do that, and that would work because for every single letter you'd have 10 to the fifth letters, and then for every single letter you'd run Jigsters on it, which I think for one letter is approximately v squared, which is like 500, and then the length of the array is like 10 to the fifth. So this would still like pass, but it would be a lot slower because you're basically always going to have repeated work. So the easiest thing to do is just pre-compute all of your shortest paths, and then once you pre-compute all your shortest paths with Jigsters, it's very, very easy. We just literally just check like from this letter to this letter, does it exist? If it does, give me the value, and that's pretty much it. So we can look at the code. So here we have our original graph, right? And if you want to actually maintain these indices, right, because original, changed, and cost are at the same index, so the original letter at I change to change that I, cost that I, you can use a zip in Python, and then you can get these three values at the same index. So essentially, like I said, our graph is just going to be a default dict of dict, where it's going to be format of the graph is going to have start nodes, and then each start node will have a dictionary of end nodes, and then there will be a cost. Then we create our Jigster graph, which is exactly the same format as this, and then for every single start node in the graph, we just run Jigsters to every single point we can get to. So we create a heap, or literally just normal Jigsters, and then you just, instead of having a visited set, you just check, is it already in our Jigsters graph? And if it's already in our Jigsters graph, that means we visited it already and we already have the shortest path. So that's that here. And then we literally just keep doing it until the whole heap is empty, and we do that with every single start node. So then we have a Jigsters graph, and then from there it's very easy. We just, for every single source and target, we literally just check like, okay, if the 2 points are the same, we don't want to calculate a distance, right? So if we're going from like A to A, we don't want to calculate a distance, but for everything else we do, right? And so if the point we're trying to convert to is not in the Jigsters graph, that means we can't get from start to end, right? Because this would have a shortest path value. So if it's not there, return -1. Otherwise, just give me the value and keep adding to the result and keep adding to the result and return it. And we can run that. And it's pretty fast. And like I said, to run Jigsters is approximately, assuming all of your edges are like, you have as many connections as possible, right? Where every edge is every node is connected to like every other node or close to it, then Jigsters will take approximately O of v cubed log v. It's like v plus e, but e is v squared. So yeah, so it's going to be v cubed log v, but because you only have 26 characters, that's just 26 cubed, which is like nothing. And then log 26 is like nothing as well. So it's going to be very small to run Jigsters. And then finally, we have to run through our. So honestly, you could argue this is O of 1 because no matter how long your string is, this is only going to be this big, right? Like you can only have so many paths. So that's totally fine as well to argue. So maybe we can say like in reality it would actually be O of the length of these connections because we have to process the connections. So it might be like the process of O of edges plus O of n of the actual, like we have to process the actual string. So that might be probably more accurate because to actually run the Jigsters part once we have the graph is it's constant time, but it's a big number, right? It's just 26 cubed. So I think this seems pretty good. And for the space, like I said, you can probably honestly say it's O of 1 because we only have 26 letters. So it's going to be like 26 squared or something for our space, right? This graph is 26 squared. This graph is 26 squared. Our heap can only have 26, I think 26 squared as well or something items. So yeah. And yeah, so I'm going to argue that like all the actual Jigsters part is O1 because like I said, you only have 26 letters, so you can have billions and billions and billions of characters in your string, and it's not going to matter. And yes, that's going to be all for this one. And so now we just have the last problem to do. So I'll be probably doing that tomorrow. So if you did like this video, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks.